In this video, we're going to be looking at inverse trig functions. But I think before we look at inverse trig functions, I should remind you a couple of things about inverses. I always like to start with the idea of the inverse in the first place. So I'm going to talk about finding inverse values. So if f of x is x squared plus 1 and g of x is 2 over x, we're going to find f inverse of 10 and g inverse of 10. Okay, so when we see f inverse of 10, we're going to set f of x equal to 10 and start solving. So I'm going to get x equals plus or minus 3. And, x is f inverse of y, so f inverse of 10 is equal to negative 3 and 3. And I'll say that again about x is f inverse of y here in a minute when we go to find an inverse function. Okay, but this thing where f inverse of 10 returned two values, that's not what we're going to be interested in for AP Pre-Cal. We're going to be more interested in the case like g inverse of 10. Okay, and when we set g of x equal to 10 and we start solving, okay, we would end up getting x equals 1/5, one value only. And so that would be g inverse of 10 equals 1/5. And that's the situation we're familiar with in AP Pre-Cal. All right, now let's find an inverse function. And this is where I'm going to remind you that, I like to think about y equals f of x and x equals f inverse of y. And really stick to that and let that guide us through our process rather than just doing kind of something mindless that I'm not even going to say. So I'm going to define f of x, and I'm going to ask you to find f inverse. So f of x equals e to the x plus 3. Okay, this is where I'm going to say, okay, I'm going to first mention, because I'll have more to say about domain and range, as we move on. The domain of this function is all real numbers. I can plug anything in I want for x, but the range is always going to be a positive number because e to any power is always positive. It can be close to 0, but it is always going to be positive. Okay, so now I'm going to replace f of x with y. And then I'm going to start solving for x, kind of like I did before. Okay, so I'm going to need to get the x plus 3 down out of the exponent, and I'm going to use a natural log here. Okay, take the natural log of both sides, apply that log property that's going to give me just x plus 3. Really, I guess that's a fundamental identity of logs. And then I'm going to solve for x by subtracting 3 from both sides. Then I'm going to say, okay, once I've solved for x, x equals f inverse of y. And so that's going to be equal to natural log of y minus 3, and I've got a function. Okay, and so if I wanted to, for some reason find f inverse of x, because maybe you were requested to, that's where we would just, f inverse of y is natural log of y minus 3. That means f inverse of x is equal to natural log of x minus 3. And then if we think about domain and range of the inverse, okay, what I need you to remember from last semester was that the domain of the inverse is the range of the original, and the range of the inverse is the domain of the original. Okay, so domain of the inverse would be, all numbers greater than 0, so 0 to infinity. And then the range of the inverse will be the domain of the original, which is all real numbers. And if you look at that, okay, remember, log functions, they can only take in positive numbers, so that makes sense. We would see a domain 0 to infinity, and then the log outputs, well, it can be all sorts of things, especially if you remember what the graph looked like. So that range is negative infinity to infinity. Now for inverse trig, say suppose f of x equals sine x, find f inverse of 1/2. Okay, we're going to set f of x equal to 1/2, and that's going to be sine x equals 1/2, and we know how to solve this equation. We've spent a bunch of time solving equations like these. Okay, so we go to the unit circle and we say, all right, sine x is the vertical displacement from the x-axis. I'm going up by 1/2, which is not very far on the unit circle. I'm going to draw it a little exaggerated, and that's going to give me x equals pi over 6. But also x equals 5 pi over 6. So already we're running into that same situation we ran into when we solved the quadratic and we had plus or minus 3, that the inverse is going to be troublesome. But we said we weren't going to deal with that like that in AP Pre-Cal. So, and then we realized that any coterminal angle to pi over 6 or 5 pi over 6 is also a solution to this angle. So it just gets worse and worse, and so we're going to need to do something about it. What we're going to do about it is we're going to restrict the circle to only certain parts where we're looking for solutions when we're solving equations like these using an inverse function for sine. And I'll show you what I mean using the graph of sine x also. Okay, so I'm going to start by sketching the graph of f of x equals sine x over the interval negative 2 pi to positive 2 pi. Okay, so I'm going to start by, kind of drawing a window. And then I am going to point out that the upper and lower y levels of this are going to be 1 and negative 1. Okay, and that's going to be important for us later. And then I'm just going to sketch some graph. And so I'm going to sketch from 0 to 2 pi, and then from negative 2 pi to 0. And then I'll, have myself a sketch of the graph of f of x equals sine x. But if I think about what just happened with, finding f inverse of 1/2, what I was really doing on the graph was I was going to, where y equal to half, and I was kind of scanning for solutions, and I ran into, multiple solutions. Okay, I've got this one here where x equals pi over 6. The line didn't quite connect. And also we found 5 pi over 6, but we knew there was others. And so what we need to do is we need to restrict the domain of sine in order to construct an inverse function. That brings us kind of to our first question. We're going to ask you questions like this in AP Precal. What is the length of the largest interval of input values of f on which an inverse function can be constructed? Okay, now this basically will happen if, when I go side to side from a half, for example, I'm only going to hit the graph once. And what's causing this graph to run into that blue line multiple times is the fact that it's turning around. Okay, the fact that it's having local extrema, okay, the fact that it's increasing and decreasing. Okay, we would need the function to be either only increasing or only decreasing. So we could look at an interval like that. That would be an interval on which, the function's only increasing. It's running from negative 1 to 1. It's covering all of its values, and it's only going to hit the blue line once. But that's not the only interval we could have chosen. We could have chosen this one also, and if we'd only looked at the graph there in green, okay, we'd still only run into the blue line once. Okay, but either way, if we look at both of these intervals, these are the largest intervals that I can come up with where the function's either only increasing or only decreasing. Okay, both of these are half the period. Okay, and so, it's like a little bit offset, but you can see from minimum to maximum, that's half the period. And so that's going to be half of 2 pi, which is pi. But to give you a little bit more information on this, a little bit of the math behind it, I would tell you the vocabulary word here that I think is appropriate for this level, without getting into one-to-one and onto and stuff, is going to be that f is monotone. And when I say f is monotone, I mean that f is either strictly increasing or strictly decreasing over an interval. And that'll be, an interval on which an inverse can be constructed. All right, so here's a quick example of what I'm talking about from the back of the notes packet. So the graph of the sinusoidal function f is given in the xy plane. What is the length of the largest interval of input values on which an inverse function for f can be constructed? Okay, well that just means, we're looking for an interval on which it's going to be either only increasing or only decreasing. Okay, that would be right here. Just go from the maximum to the minimum, or the minimum to the maximum if it's a sinusoidal function, because we know what those, we know what they're up to. Okay, and this is going to be going from 0 to 3, and so that's an interval of width 3. All right, now back to the inverse, domain restriction issue. I'm just going to tell you right now, and then I'll show you, some diagrams that I think will help make more sense, especially in light of what we did at the very beginning. In order to make an inverse function for sine x, we're just going to need to restrict the domain, and we're going to agree that we're going to use the yellow interval. Okay, mostly because that's just what everyone else uses. And like if you type something into inverse sine in a calculator, that's the interval it's going to be working off of. Okay, and I'll show you what we mean by working off of here in a few minutes. All right, so that's going to be negative pi over 2 to pi over 2. The domain of cosine that we want to restrict to is going to be 0 to pi, and again, I'll draw you a diagram here in a second and show you why that would be a good idea. And then for tangent, if we want to create inverse tangent, we're going to restrict the domain from negative pi over 2 to pi over 2. And notice that we're not going to include those endpoints. And again, I'm about to show you why. So on the next page, if we look at this and think about it in terms of the circle, and think about what I just said about, okay, if we're going to construct an inverse function for sine, we're going to restrict the domain of sine to be negative pi over 2 to pi over 2. Okay, if we do that, and we look at the circle, and just think about theta being between negative pi over 2 and pi over 2, we're going to get all of the possible outcomes for sine. All of the values between negative 1 and 1 will be hit for sine because sine is the vertical displacement from the x-axis on that interval. Okay, and then for our cosine, if we think about, okay, 0 to pi, we're going to see the same thing. We're going to see we've covered all of the possible outcomes for cosine, the horizontal displacement from the y-axis on the unit circle, all the way from negative 1 to 1. We've covered it. And then for our tangent, okay, that one's a little trickier, and I'm just going to color that in and show you this. That's the diagram. But what I will say about this, because we want negative pi over 2 is less than theta is less than pi over 2, right, not including those endpoints, is because tangent theta does not exist at those points. All right, now before we go on and start really using these inverse trig functions, I just want to go back, and I've already shown it on screen, but I haven't really heavily emphasized it, myself in this video, is that, we can represent inverse trig functions with the inverse notation or with the arc notation. Either way, I'm going to probably mostly call it arc sine, but I sometimes call it inverse sine, and you need to know those are the same thing in this class. Okay, so you need to know that arc sine or inverse sine of x is equal to arc sine of x for any x, okay, for which this is defined. And also, I suppose that you need to know that these are the inverse functions for like sine and cosine and tangent. That's what we mean when we say arc sine or inverse sine. It's the arc whose sine is, whatever. But I'm going to show you what I mean by that right now. Now, I know these problems here say, like, what quadrant does the value live in, but I just want to get right to it and actually find these values as well. So when we're confronted with a value like inverse sine of 1/2, this is something we're needing to evaluate in this class. Okay, so what we're going to think to ourselves is, where on the unit circle is sine theta most obviously equal to 1/2? Okay, so in order to think about that, I think I should draw you a unit circle, and we should look at it and think about it. Okay, now I just said that when we're operating inverse sine, we're going to restrict the circle to only the right side. Okay, so that's over here. And then we're going to say, all right, if we're finding where sine of theta equals 1/2, sine is the vertical displacement from the x-axis, so that's up there 1/2, and I'm going to draw it a little bit exaggerated so I know exactly which theta value I'm looking at. And then I'm going to look on the yellow segment of the circle, where is that y-coordinate going to equal 1/2? And it's going to be, right about there. And then I think to myself, well, really, that's what I mean by most obvious. I was going to point that out also. When I say most obviously, that's probably what I'm going to be talking to you about next year in calculus, in the rare instance that we have to evaluate one of these things. Inverse tangent of 1, that one comes up from time to time in AP calculus, and that's where on the unit circle is tangent theta most obviously equal to 1, and that's a question we'll answer later in this video, I'm sure. Okay, but so when I say most obviously, I'm talking, that's what we're doing when we restrict the circle. And so we're going to say, all right, that looks like theta equals pi over 6. That's a 30-degree reference angle. That makes sense thinking about the underlying triangle. And so if theta equals pi over 6, we're going to say arc sine of 1/2 is equal to pi over 6. So to answer the question, what quadrant does this value live in? Pi over 6, that's in the first quadrant. Just to remind you there in blue, so I'll just say quadrant 1. Okay, now if we're confronted with something like arc cosine of negative root 3 over 2, this is going to be exactly the same process of what we just did. We're going to say, all right, where on the unit circle is cosine theta most obviously equal to negative root 3 over 2? Okay, so we get ourselves a unit circle. And for arc cosine, we need to remember what we drew up above, that we're going to restrict the circle to the top half. Okay, and along there, we're saying, okay, cosine horizontal displacement from the y-axis is negative root 3 over 2. That's almost all the way to the edge of the circle. I'm just going to kind of mark it there. Okay, I recently learned that it's almost 0.9. Okay, so it's really far over. Okay, so maybe I haven't been exaggerating all that much. And then we go and we look for the spot on the unit circle in the light green segment that has that x coordinate, and that's going to be right about there. And then I say, okay, that looks like 5 pi over 6, right? And that would make sense. That would where I'd have a 30-degree reference angle short of pi. So that'd be pi minus pi over 6 is theta equals 5 pi over 6. And so if I get theta equals 5 pi over 6 in that, zone we're interested in, that's going to be arc cosine of negative root 3 over 2 equaling 5 pi over 6. And if I was going to say what quadrant this value is in, that's 5 pi over 6, that's in the second quadrant. And while we're at it, I figure we do an arctangent. So arctangent of negative 1, we're thinking where is tangent theta on the unit circle equaling negative 1? Okay, so we draw ourselves a unit circle, and since it's arctangent, we're going to restrict the part of the circle to over here, right? Not including the top or the bottom, but everything on the right side. Okay, and then I'm going to think, okay, tangent theta equaling negative 1. Well, tangent is going to equal 1 when sine and cosine, have the same length, right? The two legs of the triangle are equal, opposite over adjacent. They just have opposite signs. So, restricted to this right side of the circle, I'm going to say it's going to be down here. And, y'all are really good at normally knowing that this is 7 pi over 4, if we're thinking 0 to 2 pi, but we're not thinking 0 to 2 pi here. We're thinking negative pi over 2 to pi over 2. And so we're going to need to, right now, be thinking of this as theta equals negative pi over 4. And then, okay, now that I've found theta in the zone we're interested in, that'll be arctangent of negative 1 equaling negative pi over 4. And, about the quadrants, I'd say, all right, well, that's down there in quadrant 4. All right, now this next one, we look at arc sine of negative 0.3, and we think to ourselves, all right, sine theta equals negative 0.3, but that's not a number that we know of from the unit circle. We're not familiar with that. Okay, so the best we can do here is just, say what quadrant it's in. So I'm going to draw a unit circle and say, all right, arc sine, restricting to the right side. And, where is sine equal to negative 0.3? Well, sine's that vertical displacement from the x-axis, so it'd be down there, negative 0.3. I look over at the yellow part of the circle, and I say, okay, it's right there. And that's in quadrant 4. And that's about all I can say about that one. Okay, now, inverse cosine of e divided by 3, that's weird. Okay, we're just going to do some inverse cosine, so we're going to draw our circle and restrict the circle to the upper half because we're doing inverse cosine. And I just need to remind you about e, I just figured it'd been a while. We need to talk about it. We need to start reviewing for the AP exam before too long, and so this is, I'm just going to mix that in. A little bit of e talk here. So I just need to remind you, or maybe I'd like for you to think before I remind you, what two numbers is e between? Okay, what two whole numbers? E is between 2 and 3. Okay, so if I think about e divided by 3, well then that's just going to be between 2/3 and 1. Okay? And so I'm just going to mark off some spot where I think cosine is between positive 2/3 and positive 1. And I think that's just going to be right there. And then I'm going to mark the spot in the light green sector where we're having that x coordinate, and that would be right about here. And then I would say, all right, that's there in the first quadrant. All right, now this one's not in the notes, but I do want to kind of run this at you and see what you think about it. Inverse cosine of 3 over e. Okay, what we would say is, all right, we're looking for a spot where cosine theta equaled 3 divided by e. But remember that e is a number that's between 2 and 3, so this number is bigger than 1. And cosine of theta, that's between negative 1 and 1 for all theta. Okay, so this is not going to be possible. Right? We can't take inverse cosine of a number that's bigger than 1 or more negative than negative 1. So I'm going to say that this does not exist. Now, with that said, I'm going to ask you about arctangent of 999. And you might be sitting there thinking, oh, well, that one's not going to exist either because 999, that's way bigger than 1. Okay, but tangent, if you remember the graph of tangent, okay, which I'm not really going to get into here because we'll talk about graphs in the next video. If you remember tangent, it had these vertical asymptotes where y went up to positive infinity and came from negative infinity. So tangent can kind of cover all the real numbers. Arctangent, you can put anything you want into it. So I think about the unit circle and for arctangent. And so I restrict the area to the right side and don't include the top or the bottom. And I just want to remind you about what happens to tangent theta as theta approaches pi over 2 from below. Okay, remember that notation. Okay, as theta approaches pi over 2 from below, x is getting closer to 0, but it's a positive number, and y is approaching 1. So as we're getting closer to dividing by 0, okay, our output, tangent, y over x on the circle or opposite over adjacent on the underlying triangle, that's going to approach positive infinity. Okay? So if I'm thinking about arctangent of 999, that's a really big number. That's going to be really close to pi over 2. And honestly, it's probably going to be a whole lot closer than that, because if you think about the underlying triangle, if you were to draw the triangle, down to the x-axis, the ratio of opposite to adjacent would not be 999. It would be 999 if I got really, really close to pi over 2. But all that said, that's happening in quadrant 1 because tangent's positive up over there. You can do the all my students take calculus thing, but I don't think that's really all that necessary for AP Pre-Cal. So I'm just going to kind of, take these, problem by problem and just attack them as I see them. Okay, now I think it's time for you to do some practice on your own. Find these arc trig values. Do this with the video pause because I'm just going to bring in the answers here in a couple seconds. All right, there you go. These were some good examples, definitely good practice for you, exactly what you need. But what I wanted to emphasize, especially with the last one, that one 20 minutes in or so, is just once again, when we're evaluating inverse trig functions, what we're trying to do is find an angle that corresponds to a given trig ratio. Okay, so for something like arctangent is 0, when we find that spot over there, and that's 0. What we're really saying is it's a 0 radian angle that corresponds to tangent equals 0, most obviously on the unit circle. All right, now I got just a couple more examples for you about inverse function values. It's got a couple of equations. And so let g of x equal cotangent x. What are the solutions to all solutions to the equation g of x equals 1/5? Well, I'm just going to start by setting g of x equal to 1/5. That's cotangent x equals 1/5. And I don't know a whole lot about cotangent. I'm going to write this in terms of tangent. That would be where tangent x equals 5 over 1. This is going to be 5. And, okay, I don't know any special right triangle in the unit circle or any spot on the unit circle where tangent is going to equal 5. That's just not a unit circle number that I know. So, best we can do to get an exact answer is to take inverse tangent of both sides and say x equals inverse tangent of 5. Okay, but to, point out on the unit circle where I think that is, well, 5's, pretty big for a trig ratio, so it's probably pretty close to pi over 2. Like I was saying earlier, where it's arctangent of 999. Okay, or tangent does most of its growth right in the last moments before pi over 2. Okay, and, but it's asking for all solutions, and so I'm thinking, okay, there's going to be a place in the third quadrant where tangent x equals 5. So, that'd be around there. We remember the, period of tangent, and therefore the period of cotangent is going to be pi. And so these solutions to tangent equations, they repeat themselves every pi. Okay, but if I want all solutions, really what I'm looking for is the general solution. So I'm going to say x equals inverse tangent of 5 plus pi n, where n is any integer. Okay, now I got one more example for you, and this one, I will admit, is a little bit tricky. Okay, but we've got a lot of examples like these on the homework, so, I'm just going to do this one the once. So for what value of x on the interval pi to 2 pi does f of x equal 0? Okay, and f is 8 plus 9 cosine x. So I'm just going to start solving algebraically, set the thing equal to 0, subtract 8, divide by 9. Okay, cosine x equals negative 8 over 9. I don't really know that from the unit circle. It's not a special right triangle or anything. So I'm going to need to take inverse cosine of both sides. And I'll say x is inverse cosine of negative 8 over 9. But there's an issue with this. If I look on the unit circle and I think about, okay, what just happened here? I just took inverse cosine of negative 8 over 9. So I'm looking horizontally where I'm at negative 8 over 9 on the x-axis. Find the spot on the unit circle. That is not on the interval pi to 2 pi. That's in the second quadrant. Okay, we're looking really in the third and fourth quadrants. Okay, so that's going to be an issue for us. Okay, so what we're going to do is we're just going to think about, okay, our cosine or inverse cosine of negative 8 over 9 is really representing that much angle, that much rotation. And there's another place on the unit circle that has that x-coordinate, right? Down here in the third quadrant, the place that we're really looking for, this real solution on the interval pi to 2 pi to f of x equals 0. So what we're really looking for is that much rotation. Okay, so, I think it would be natural to think, oh, well, the negative of inverse cosine of 8 over 9. But that would be, again, a negative number and not in the interval pi to 2 pi. So we're going to be able to get that by thinking of the far right edge as 2 pi and thinking I'm subtracting from 2 pi. 2 pi minus the inverse cosine of negative 8 over 9. And so that's going to be the solution that's on the interval pi to 2 pi. And I will admit that one is a little bit tricky, but I think if you do the practice problems on the homework, you'll get the picture. And so I think that's all I've got to tell you about finding inverse trig values. Okay, I'm going to come back in a separate video and show you about the graphs of inverse trig functions, and that one will be much shorter than this one. So that's all. Thanks for watching.